last time when I did a presentation, I talked about linear regression, which is a type of regression you use when you have a continuous outcome. And I also talked very briefly as well about confounding and how to deal with confounding in your models. So today I thought I'll talk about logistic regression, which is a type of regression you use when you have a binary outcome. And also I'll briefly talk about effect modification, which is what happens when a third variable changes the relationship between your exposure and outcome. Okay, cool. Oh, what I should say before I start is I try very hard in these presentations to not show you all too many equations and things, but for logistic regression, I kind of do have to show you some equations and talk about exponentiating things and stuff. And I'm really, really sorry about that in advance. It's just, I just kind of have to. I'm really sorry. Okay, cool. Does anybody want to say anything before I start? Okay, cool. I'll just continue. Right. So imagine we want to find out what the relationship is between obesity and high blood pressure. So we go out on Tottenham Court Road and we measure BMI on about 7,000 people, and we classify them as either non-obese or obese. And we take their blood pressure and we classify them as either having high blood pressure or not having high blood pressure. And we just draw this simple 2x2 table of obesity by high blood pressure, and we group people into each category, yeah? And we can see that among the non-obese, which is this group here, yeah, the prevalence of high blood pressure is 13%, okay? So 651 people out of 4,994 have high blood pressure when they're non-obese. And then among the obese, 30% have high blood pressure, okay? Now, I wish I could tell you that we can easily compare the prevalence of high blood pressure among the obese and non-obese, yeah, because that would make everyone's life easy. But unfortunately, we can't compare prevalences very easily because they don't really have some very nice statistical properties that odds have. And so instead of talking about prevalences, that's why we talk about odds, because odds have nicer statistical properties than prevalences, which is like really kind of annoying, but it's just the way it is, I'm sorry. So, well, what is an odds? And to be honest, I never knew what an odds was until I did like my master's, because I think they only talk about odds really in betting and in statistics and nowhere else. So the odds of high blood pressure among the obese is the number of people who have high blood pressure, the odds of high blood pressure among the non-obese is the number of people who have high blood pressure and are non-obese, so 651, divided by the number of people who are non-obese and don't have high blood pressure. So that's 4,343. So the odds of high blood pressure is going to be 0.15. Then the odds of high blood pressure among the obese, likewise, is going to be this 772 divided by 1,778. So it's the number of people who have high blood pressure and are obese divided by the number of people who don't have high blood pressure but are obese. And that is 0.43. So then the odds ratio of high blood pressure comparing the obese to the non-obese is simply just dividing this odds of high blood pressure among the obese divided by the odds of high blood pressure among the non-obese. And that works out to about 2.9. So what that means is the odds of high blood pressure is 2.9 times higher among the obese compared to the non-obese. So loosely speaking, your chance of having high blood pressure is much higher if you're obese compared to non-obese. Yes? Is that clear? Okay, cool. If anybody has any questions, just interrupt at any time. So I've just rewritten this odds of high blood pressure that we worked out up here. And I've shown you how to calculate the odds ratio now with a 2x2 table. But you can also calculate the odds ratio using something called a logistic regression. And like I said at the start, a logistic regression is the type of regression you do when your outcome, in this case, high blood pressure, is binary. So in my stats package, I can put in, I type this. So I say, do a logistic regression with high blood pressure as my outcome and obesity as my exposure variable. And this is what comes out from my stats package. And these numbers come out and it's like, well, that's weird because these numbers don't correspond to the 2.9 odds ratio, yeah? And the reason for that is that a logistic regression is done on a log scale. So what this logistic regression is spitting out to us is saying it's the log odds of high blood pressure is equal to the constant, which is minus 1.9, plus this coefficient for obesity, 1.06 times whether you're obese or non-obese. Okay. Now, somehow from this equation, we're supposed to end up with an odds ratio of 2.9. So I'm going to talk you through now how we end up with that. Okay. So all I've done here is given back the output from the previous slide, and I've written this back down to remember that we want to get to this odds ratio of 2.9 from our logistic regression. And I've just written down the equation, which comes out from the output from the logistic regression that I've done on the computer. Okay, so if I try to now find what is the odds of high blood pressure when you're not obese? So that's simply this value, this variable obese takes the value of 0, and the log odds of high blood pressure among the non-obese is minus 1.89. Similarly, the log odds of high blood pressure among the obese is minus 1.89 plus 1.06, because this now takes a value of 1. So if I minus these two log odds, I end up with the log odds of high blood pressure among the obese minus the log odds of high blood pressure among the non-obese is this minus that. So this minus 1.89 cancels off and I'm left with 1.06. Now here is where I need you to remember your laws of logarithms. Specifically, I need you to remember that log x minus log y is equal to log of x divided by y. So basically, if I apply it on to this, it's log of something minus log of something else is equal to the log of the ratio. Okay, now this log of the ratio, this is the odds of high blood pressure among the obese divided by the log of high blood pressure among the non-obese. So this is the log odds ratio for high blood pressure comparing obese to non-obese, and that's equal to 1.06. So if I exponentiate both sides, I end up with the exponential of 1.06 is 2.9. And that's what we found from that 2x2 table right at the start, that the odds of high blood pressure comparing the obese to the non-obese is 2.9. So the main point of the story is when you get your output from your logistic regression and you have your coefficient, what you need to do is you need to exponentiate your coefficient of interest to get the relevant odds ratio. So I just need to exponentiate this coefficient 1.06 and I'll get the odds ratio of 2.9. Now, when you do your logistic regression, you do get these coefficients, but because you need to exponentiate it, most statistical packages will exponentiate your coefficients automatically. And in my stats package, I can do it by giving this option comma OR. And what that does is it gives me results on an odds ratio scale. So here, I can look at it right away and say that the odds ratio comparing obese to non-obese for the outcome high blood pressure is 2.9. Yeah, so it depends on how you've done your logistic regression. If you've done it on the log odds scale, you have to exponentiate your coefficients. If you've done it on the odds ratio scale, you can read it out right away. But essentially, it's important to realize that the regression equation that you fit is exactly the same in both situations. It's just that in one case, you're getting results that need to be exponentiated. In another case, you're getting results exactly on the odds ratio scale. And you need to know which one you've done. Yeah. So what I've shown you so far is I've shown you this neat little 2x2 table, and I've been able to calculate an odds ratio from this nice little 2x2 table. And then I've gone and confused you all and shown you this logistic regression and being on an odds ratio scale or a log scale and exponentiating and things to get exactly the same results from as I did on a 2x2 table. So you're probably going to be like, well, seriously, why am I going to bother with a logistic regression when I can get these results from a 2x2 table? Because it's so much easier. The reason that you want to bother with a logistic regression is for several reasons, but two main reasons. One is, for example, confounders could be affecting the relationships. Yeah. So, for example, socioeconomic position can affect whether you're obese, and socioeconomic position can also affect whether you have high blood pressure. So it could be a confounder. And you can adjust for that confounder in a logistic regression, but you can't necessarily adjust for that confounder in a 2x2 table. Yes? Likewise, effect modifiers. You can deal with effect modifiers in a logistic regression, but you can't deal with effect modifiers in a 2x2 table. And that's why you need to be bothered with logistic regression rather than just a 2x2 table. But just like in terms of practical advice, what I would do is if I have my data set, before I even fit the logistic regression, I would just draw out the 2x2 table, calculate what the odds ratio is, see if I can get the same thing in my logistic regression, be confident in the results of the simple logistic regression, and then start building up the logistic regression to account for confounders and effect modifiers and so on. Before I continue, I just want to make sure that everybody follows what I've said so far. And if there's anything to clear up, please, can I just do it now, because the next bit's going to get a little bit more complicated. Any questions?
Snehal, can I ask an extremely basic question quickly before you carry on? Based on that 2x2 table you've shown us, yeah. If you wanted to ascertain whether there was a statistically significant difference in rates of high blood pressure between obese and non-obese, can you just do a chi-squared on that? Yes. Or is that any different?
Absolutely. Your chi-squared test in this 2x2 table is going to give you exactly the same results as this p-value from the odds ratio, but that's because I haven't accounted for confounders or effect modifiers or anything. In the very basic instance, they're doing almost the same thing.
Yeah, okay, fine, cool, thank you.
Anybody has another nice simple question? The difficult questions, don't bother asking. Okay, I'll take the difficult questions now. No? Okay, fine. Right, so I want to just talk a little bit about effect modifiers, yeah? So the way we have calculated obesity in this data set is based on BMI, okay? Now, BMI doesn't really do a very good job. It does a terrible job at differentiating between fat mass and lean mass, yes? And especially in men, obesity, it's likely that men who are classified as obese probably have a lot of muscle mass. So for example, the whole of Arsenal football team apparently are classified as obese, yeah? And so, whereas in women, women who are classified as obese tend to have more than men. So he's probably doing a good job at defining like adiposity in women, but less so in men. So the relationship between obesity and high blood pressure might vary by sex. So that's the next question that we're going to try and ascertain. Is the association between obesity and high blood pressure the same in men and women? And the way we do that in a logistic regression is by modeling something called an interaction. So the way we do that in our model is we tell the computer again, we're doing a logistic regression with high blood pressure as our outcome. We're interested in obesity as an exposure of interest. We want sex in our model, we're males or females. And this thing here basically says we want to include this extra term, which is obesity multiplied by sex. Okay, so we have four coefficients in our equation now. So we have the log odds of high blood pressure being the constant, minus 1.51. plus the coefficient for obesity, 0.86, plus the coefficient for sex, which is minus 0.88, plus this extra bit, which is 0.59, which is the coefficient for obesity times sex. So that's the extra, if you want to think about it, loosely speaking, it's the extra bit of effect that happens when you're obese and you're female. Yeah, because over here, sex is 1 if you're a female. So this equation does look quite long, but we're going to try and break it down to understand what it really means. So if we just look at males in the first instance, that will be fairly straightforward because this bit of the equation drops off and this bit of the equation drops off because sex is 0. And we end up with the log odds of high blood pressure is minus 1.51 plus 0.86 times obesity. Okay, now remember, previously we talked about the log odds of high blood pressure among the non-obese being minus 1.51 because obesity is 0 here, and the log odds of high blood pressure among the obese is minus 1.51 plus 0.86. And then remember, we minus these two to end up with 0.86. And when we exponentiate it, we'll end up with 2.37s. Yeah, this is just a recap of before, because basically, once we get to this equation over here, we just remember that we need to exponentiate the coefficient for obesity to get the odds ratio for high blood pressure comparing the obese to the non-obese. So this middle bit I just put into recap, but really once you see this equation over here, you can almost jump straight to this last this last section here, which I'm going to do with the females now. So when you're looking at women, sex is 1. So what we now need to do is we need to gather the similar coefficients together. So when sex is 1, the log odds of high blood pressure is minus 1.51 plus 0.49, no, plus minus 0.88, which is minus 2.39. And then we need to gather the coefficients for obesity together, which is 0.86 plus 0.49, which is 1.35 multiplied by obesity. Now remember what I just said, once you get to this equation over here, you just need to remember that the log odds ratio comparing high blood pressure for obese to non-obese is 1.35. So if we just exponentiate 1.35, we get the odds of high blood pressure comparing obese to non-obese in women as 3.87. And this is saying that the relationship between obesity and high blood pressure is stronger in women than men. And that's exactly what I kind of hypothesized on the previous slide, because obesity in women is much more about body fat percentage, whereas obesity in men is a mishmash of body fat percentage plus lots of muscle mass. And so you would expect that the relationship between obesity and high blood pressure to be lower in men than women. And so in this case, there is effect modification by gender. I mean, yeah? So what we did before now is we were able to find the odds ratio for obesity, comparing obese to non-obese in men, is this coefficient, which we exponentiate to get 2.37, okay? And then for women, we have to exponentiate this coefficient for obesity plus this extra bit that you have to add on because you're a woman and you're obese. Yeah, so it's 0.86 plus the extra bit of 0.49, which is the odds ratio of 3.87. Okay, so this is exactly the same as what I showed you on the previous slide, but just to re-emphasize that this has been done on the log scale, where we then need to start exponentiating things. Your statistical package is most likely to be able to give you the same results on the odds ratio scale. And if it gives it to you on the odds ratio scale, the way to interpret it is like this. So the odds ratio for high blood pressure in men comparing obese to non-obese just drops out of the equation. It will be 2.37. And then the odds ratio for women is going to be this, and this extra bit because you're obese in a woman. But now you're not adding it. You have to multiply them multiply the odds ratios together. Okay, so it's just, again, emphasizing the importance of knowing what scale you're getting your results out on, because if it's on the log scale, you have to add things together and then exponentiate. If it's on the odds ratio scale, you just multiply things together. So you need to understand what you're fitting and what's coming out in order to interpret it correctly. So again, I want to convince you that doing an interaction in this way is worth doing, because I've shown you how to do an interaction in this really complicated way, multiplying things and then like exponentiating stuff and everything. And you'd probably be like, well, honestly, I can get the same results by just stratifying my analysis. I can just stratify my analysis with this condition saying, do my logistic regression if I'm only considering males, or do my logistic regression if I'm only considering females, and I can get my odds ratios. And I agree, like doing it like this is like 500 times easier than doing it in the way that I showed you at the beginning. But doing it with an effect with an interaction term is more efficient and better. Well, I shouldn't say better, but it is better than doing a stratified analysis. And the reason for that is because when you're doing a stratified analysis, you're forcing an interaction between sex and all explanatory variables. So for example, if our regression equations contained socioeconomic position as a confounder, when I stratify my analysis and I consider only men or I consider only women, I'm forcing the effect of socioeconomic position to vary by gender. Whereas in my original analysis, I can decide whether a relationship should vary by gender or not. Yeah. And also on a practical level, if I do a stratified analysis like this for males and this for females, I can't say with any certainty that the odds ratio of 3.86 is different from 2.36. You can't compare these two odds ratios, whereas when I do an interaction like this, I can, because see this value over here, this is the value, the extra bit of effect that happens when you're a woman and you're obese. And the p-value for that extra bit is less than 0.01. And so I can say from this interaction analysis that the effect varies by gender. Whereas if I do a stratified analysis, I can't. Okay. Does anybody have any questions? Because I appreciate that this is actually quite complicated. Okay, cool. The last slide here that I want to present is exactly the same as I did with the linear regression presentation, but it's worth repeating because it is so important. So first things is that you shouldn't extrapolate from the data that you have. So in my data set, although I haven't shown it to you, I think obesity was defined up to a BMI of about 35. And so you shouldn't really extrapolate beyond that because you don't know what the relationship is like in unobserved data. Secondly, it's really, really important to ensure that the data that you're putting into your stats package is valid. It's been measured well. There's no kind of, typos or errors or anything, because if you're putting rubbish data in, no matter how sophisticated the model you're fitting, you're going to get rubbish answers, basically. And finally, and guys, this is super important. Just because I've shown an association doesn't mean that it's causal. So just because high blood pressure is higher among those who are obese doesn't mean that obesity is causing the high blood pressure. And certainly in this case, because the relationships were cross-sectional, because we measured obesity and high blood pressure at the same time, it could very well be going in the other direction as well. Yeah. And that's all I had to say. And yeah, if you all have any questions, please just ask me now.